Hello, I'm Ryan Baker, and this is Big Data in Education. Today we'll continue our discussion of classifiers. So classification, as you may remember, there's something that you want to predict, the label, and the thing you want to predict is categorical. The answer is one of a set of categories, not a number. In the previous class, we discussed step regression, logistic regression, and decision trees. Today, we're going to discuss more classifiers, which are in this middle space of conservativeness. They're more conservative than neural networks, coming up, but they're less conservative than logistic regression and single decision trees. The big idea behind the models that we'll be talking about today is that if one model is good, maybe many models are even better. In other words, these algorithms are a special case of what's called ensembling, where you build a bunch of different models and then you combine their predictions together. And you can do that in a variety of ways, including voting. Every model gets a vote, every algorithm gets a vote. In that case, maybe you have 7 algorithms, and if 4 of them say 1 and 3 of them say 0, you go with 1. Averaging, where you take the confidence estimates out of each model and you average them together. Weighted averaging, where you do that same thing, but you give more weight to some classifiers than others. You could use a classifier to combine classifiers. You actually build, say, 20 different classifiers to make a prediction, and then you build a meta-classifier to weight each of those classifiers, and other fancier approaches. In ensembling, you might be using models from totally different algorithms. You might be ensembling 7 algorithms together. Or they could be the same algorithm, but on different subsets of the data. And in practice, the latter of these two, using the same algorithm but different subsets of the data, is more common, and the most popular way to do it is with trees. Broadly, there are 2 different ways to do that. The first is called bagging, the second is called boosting. And the debate between bagging and boosting is one of the great debates of classical machine learning. In bagging, you fit a bunch of models in parallel. Essentially, you just take maybe different subsets of the data or different initial parameters, and you fit a whole bunch of models that don't talk to each other. In boosting, you fit a bunch of models one after the other, and the later models try to correct the errors in the earlier models. Random forest is a type of tree bagging, where you split the training data into random subsets of data points, and for each subset, you take a random set of the data features, and you build a decision tree on the resultant data set and set of features. And then you take all the trees, and each tree gets 1 vote. Random forest is good with relatively small scale data. And among more contemporary algorithms, what's contemporary anyways, it's relatively interpretable. You can extract which features are most important to the model's predictions in a pretty straightforward way. XGBoost is kind of the classic among tree boosting algorithms these days. It's kind of taken over from earlier ones like AdaBoost. XG stands for extreme gradient, so extreme gradient boosting. XGBoost builds a lot of small trees of 4 to 8 levels on optimized subsets of the data. And what it's doing is it's trying to iteratively figure out which combination of small trees best fits the data. XGBoost has a lot of clever tricks to improve fit, including things like adding trees greedily, which means that you take the next tree based on where you are from the previous ones, and progressively shrinking the contribution of earlier trees in the sequence, and attempting to learn how to handle sparse parts of the data space, as well as denser parts of the data space, by learning better defaults where there's a lack of information for this specific data set. And it's worth noting that even though this is a classification lecture, Random Forest and XGBoost are not just for classification. Just like you can use trees for regression, you can combine them for regression. And both Random Forest and XGBoost can be used for regression. A few other classifiers worthy of mention. Decision rules. They tend to underfit, but they're great for understanding the data better. They come up with very human interpretable rules. Love them for that. You don't see them published that much, but they're great for exploring your data. K-star and KNN, an approach that takes individual data points and tries to relate to them. Sometimes uniquely successful when the data is highly divergent, but it does not scale well at all. Support vector machines, good with high dimensionality data. In order to learn more details about these classifiers, see previous editions of this course. So that concludes our second lecture on classifiers. In later lectures, we're going to discuss neural networks, goodness metrics for comparing classifiers, how to validate classifiers, and, because I've thrown around the term a bunch, what do I mean when I say conservatism? That links into another topic called overfitting. But for now, our next lecture will be a case study in classification.